specifying DSDN itself, which we should do, but it's not as interesting. And then there's the implications of this kind of architecture. More verification, and we can actually pick up here the details of DSDN once the talk goes on.
Focus. Thanks. Do folks want to move forward a little bit cozier? You can do it. So, quick announcement, our next discussion section has been permanently moved from being between 9 to 10 a.m. to 1 to 2 p.m. Same day, but so you have more later hour options. Thanks. Okay, so topic for today, we're going to start with a new topic altogether. We're done with intra-domain routing. Our topic is still routing, but in the context of interdomain, what we call interdomain routing, or routing across domains. And so far, all of the lectures you've seen with Murphy lecturing, we talked about routing on a graph that looked like this, made up of routers and links and end hosts. And if you remember, Murphy made the point that this is how we tend to do routing within a single domain. Okay? And so from now on, we're going to focus on kind of this notion of a domain, or more formally what we'd call an autonomous system, and I'm going to define that in a second. And we're not going to worry so much about the details of how routers and links are interconnected within this domain. Okay? Instead, we're going to focus on the domain as a logical node, so think of it as one node. Okay? And I'm going to represent it with clouds, just like we had squares for routers and circles for end hosts. And more generally, we're going to focus on what we call this interdomain topology, or the AS graph, the autonomous system graph. So this is kind of the end-to-end view on the internet of how different networks or different domains are interconnected. Okay. Specifically, we're going to focus on this question of how do I find a path across this AS graph. So we're finally in the realm of doing an end-to-end path across the internet, across multiple ISPs. And at the same time, we shouldn't forget that actually that path is not going through clouds. It's going through a series of links and routers that are within each of these domains. But for the most part, we're not going to talk about that in this lecture. In the next lecture, we'll get back to talking about how intra-domain and interdomain actually intersect, how they integrate. But for today, we're going to stick with this picture of I have a graph that's made up of these clouds or ASs that are interconnected. And I'd like to start by just taking a closer look at one of these domains or autonomous systems, and what is it exactly, and what is so special about the interdomain topology and autonomous systems. And so autonomous systems, I'll be using the term domain and AS interchangeably. Autonomous system is a slightly more formal term for what we've been calling a domain informally. And an autonomous system is simply a network that is under the administrative control of one entity. So UC Berkeley is an autonomous system because the UC Berkeley staff decide how to operate our network. AT&T is another AS. France Telecom, Deutsche Telekom, there are many autonomous systems or ASs across the internet. Okay? And as I said, informally, we're going to call them domains. What defines or what makes a network an autonomous system is the fact that it has been assigned a unique autonomous system number, or ASN. This is a number that's assigned by this organization called ICANN. I think Murphy talked about it in the context of assigning IP addresses. So if you want to be an AS, you have to go to ICANN, you have to make your case, and you get an autonomous system number. Berkeley, for example, is ASN number 25. Fun fact, this is John Postel. He was one of the early internet pioneers, really influential in the design of TCP/IP. And actually, in this context, until his death, he was a single person that handed out ASN numbers for the entire internet. So we had one person doing all ASN management for the entire internet. This is now, of course, this organization ICANN with lots of international laws and so on. But way back, there was this one guy handling it. Just if you're curious, how many AS ASs do we have on the internet? This is going up to 2020. I believe this number is close to 100,000 now. So that kind of tells you the scale of the AS graph. It's about 10,000 nodes. If you're curious where they go, as you can see, the US is hogging the largest number of autonomous systems. This is not surprising. Brazil is number 2, which was somewhat surprising to me. But in general, you see these handed out across the world. Okay. From our perspective, as we talk about autonomous systems, there are kind of 2 common kinds of ASs that we're going to talk about and that are important for how we do routing. The first is what we call a stub AS. This is an AS it only exists and its only job is to provide connectivity to its directly connected users or hosts. So it's not in the business of carrying traffic between other ASs. It only exists to carry traffic to and from its directly attached host. So UC Berkeley is an autonomous stub AS. Typically, you'll find that enterprises, businesses, people that are not in the business of providing network connectivity, that's not why they exist. Those tend to be stub ASs, enterprises, and so on. Okay? The other kind are what we call transit ASs. These are ASs that will carry traffic on behalf of other ASs. So these are the ASs you'd expect, AT&T, Verizon, and so on. They're kind of in the business of internet connectivity. That's their reason for existence. And in practice, we'll get to this a little bit more in slides going forward, but in practice, there's quite a bit of variance in the nature of transit ASs. So you might have a transit AS, for example, that covers California. And then you might have a transit AS, what we call tier 1 ASs, that cover the entire globe. Okay, so there's a little bit of hierarchy even amongst transit ASs. But by and large, this is an important distinction. Stub AS is only for your directly attached users. Transit ASs, you carry traffic for other ASs. Okay. So I want to talk a little bit more about that interdomain topology and what makes it unique. What makes it so different from all the graphs and topologies you've been thinking about so far is that the topology is shaped by business relationships between the ASs. So now when I say that on the AS graph, A and B are neighbors, it means they have a physical connection, just like 2 routers that had a link between them. That is still true. But it also crucially means that they have a business relationship, by which I mean they have a legal contract that defines what service they're providing to each other and how they interact. And that really determines why we have the topology we have. And so there are 3 basic kinds of these business relationships on the internet. If I take 2 ASs, X and Y, the relationships they can have with each other is you can either be a customer of another AS, or you can be a provider to another AS, or the 2 ASs could be peers. Okay? And so what does that mean? The business implication is if you're a customer, then you're paying your provider. So customers always pay providers, and peers don't pay each other. They exchange traffic, but they don't pay each other for that exchange. So as an example, you can think of Berkeley signing up with AT&T in order to connect to the rest of the internet. Berkeley would be AT&T's customer, and AT&T would be Berkeley's provider. Okay? Why do ASs peer? I will get to that in a minute. But typically, the assumption underlying why 2 ASs are peers, the reason it makes sense for them to be peers is they're kind of the same size or scale, and that they exchange roughly equivalent amounts of traffic. And this is all codified in the contracts that they sign with each other. There'll be something that says, for example, that over a month, the 90th percentile of traffic that I sent you is within 10% of the 90th percentile of traffic that you sent me. So there's some technical definition of equal traffic that's in a contract, and that's kind of how we decide that we're meeting the condition to be peers. Okay? And so let's talk a little bit now about how these affect topology. Any questions on this so far? It's pretty intuitive, I think. So we're going to look at a lot of these AS graphs. So let me walk through this a little slowly so you kind of internalize in your head what's going on here. So this is a topology with 5 ASs, A to E. And I'm showing you here the relationship between these ASs, where I have this directed arrow for provider-customer. And so you can see in this graph, we have a bunch of provider-customer relationships. And then I have a different arrow edge, which I don't have any in this right now, but we would be using this other type of edge to denote a peering relationship between two ASs. And just to put it up there so you have it, remember customers pay providers and peers don't pay each other. Okay, so in this example, D is a customer of B, B is a provider to D, but at the same time, B is a customer of A. A does not have any providers, it has multiple customers. Okay? You could map this to D could be Berkeley, B could be a regional California ISP, A could be a global AT&T. So if I looked at this graph, I would say that D and E are stub ASs. Right? They don't have any customer ASs. And A, B, and C are transit ASs. Okay? Because they're carrying, for example, B is carrying traffic between D and A. A is carrying traffic between B and C. And in general, when we draw these graphs, we're going to draw stub ASs at the bottom and increasingly larger transit ASs at the top. So there's kind of this hierarchy. Yeah. Yeah, and so in fact, inside, if you look inside AT&T, they have portions of their network where they have directly attached hosts and directly attached customers, but they're also providing transit. And so typically we would call those transit, but they are playing the role of both. Not necessarily, no. Okay, so on this figure here, I'm going to say that I think it would be a great idea for B and C to have a peering link or to have a peering relationship. Anyone agree with me? Anyone want to say why? Yeah. Exactly. So let's say D and E talked a lot, right? And that traffic has to go BAC. Both B and C have to pay A to carry that traffic. So at some point, they're going to look at their traffic and say, this is quite expensive. If we just directly peered, we would actually save money on both sides. Both B and C win by putting in that peering link. Okay, so this is why we have peering relationships. It saves money for some of these transit ASs. Any questions on that? Okay, so moving forward, let's go back to this kind of AS graph. In practice, you wouldn't have an AS graph that looks exactly like what I have up here. Instead, you would have one that looks more complicated like this, where you have a large number of these ASs at the top. And the reason is largely for geopolitical reasons. Right? Nobody wants to have this one global AS that is an American company or an Asian company. Every country wants to know that they have some set of options